Shall we start, ma'am?
Sir, yes, we can start.
Yes. Very good afternoon, participants. I hope everyone had your lunch and being ready for the session. I'd like to welcome all the participants for a day 2, session 2, AICTE sponsored 2 weeks online faculty development program on emerging trends and challenges in VLSI mixed signal processing for 4th industrial revolution. Phase 4. Welcome you all. It's my immense pleasure to welcome our today's resource person, Dr. V. Geeta, Associate Professor, Department of Electronics and Communication Engineering, Konga Engineering College, Erode. Welcome you, ma'am.
Thank you.
Every thought you produce, anything you produce, it bears your signature. I'm saying about the person who is none other than our today's resource person, Dr. V. Geeta. Before going to session, let me share a short intro about her. She completed her master degree in VLSI design from Konga Engineering College and completed her PhD in Information Communication Engineering in Konga Engineering College under Anna University, Chennai. Her main area of specialization is VLSI design. She has more than 13 years of teaching experiences and presently she is working as an associate professor, Department of Electronics and Communication Engineering, Konga Engineering College, Erode, Tamil Nadu. She published more than 15 papers in the national conferences and more than 7 papers in the international conferences. And also, she published 11 journals in the international and national journal research papers. She acted as a keynote speaker and invited guests in various conferences, workshops, and some other faculty development programs and short-term training programs. In this way, now I'd like to hand over the session to our resource person, Dr. V. Geeta, who is going to handle the session on the topic of role of analog signal processing in VLSI. Please, ma'am.
Thank you. Thank you for nice introduction about me. It's my pleasure. May I share the screen?
Yes, ma'am, you can start your presentation.
Hope the screen is visible.
Yes, ma'am, visible, ma'am.
Okay. Thank you. Good afternoon to one and all connected in the meet. So in today's session, we are going to see about the role of analog signal processing in VLSI. And I'm going to present a sample research work with mixed signal processing. So here my presentation includes what is analog IC design. Yes, it is outdated. And what are the components of VLSI microelectronics? Then what do you mean by mixed signal VLSI? Then what are the basic building blocks of analog IC design? Then what are the challenges and what are the available design tools for analog IC design? Then we are going to do a small analysis about the failure of analog designs. What are all the reasons for failure of analog designs? Then testing of analog ICs. Then the CAD tools available for analog IC. Then how the VLSI technology trend goes on. Then we are going to conclude something from this presentation. After that, I will give you a sample research work in mixed signal processing. So we will start the session with these contents. So analog IC design is the implementation of analog systems and circuits by means of IC technology. So here, VLSI is one of the growing technology which is related with the IC fabrication technology, which is moving towards the sub-micron architectures. And this is just the combination of both digital and analog on a single chip. Now, the VLSI trend moved towards submicron level of structures and the mixed signals on a single chip. So here, what are all the challenges when we are working with the VLSI design? So we know we are moving towards VLSI in order to achieve minimum area, minimum power consumption, and maximum speed. So here, when working with the VLSI design, we are having the requirement of scaling in order to achieve the target. So here, when working with the scaling VLSI, we are facing multiple challenges, which includes power dissipation, leakage power management, then short channel effects, increasing noise, and integration issues. So when working with the accommodation of more number of transistors within a small area, there is more possibility for power dissipation, and there is surely leakage power. So these are major components which creates more issues. Then when going for deep submicron transistors, we are having short channel effects. When working with the scaling, interconnection creates large problems, and this may increase noise. And when working with the mixed signal, integration of analog and digital on the same platform creates issues. So these are all the challenges when we are working in VLSI domain. So here, what is the difficulty? Why there are no more researchers and more developments in analog design? Why there is a lagging in this domain? Is what is the difficulty? So when working with the digital, we know digital is with the zeros and ones, on and off, whereas analog is continuous. So here, because of this basic difference, when working with the analog circuits, we need to consider more number of factors that affects the analog circuit. We know analog circuits are normally affected by temperature, and there are more possibility for inclusion of noise in the analog circuit, And the power signals also affect the analog circuit. So, when working with the analog circuits, we are bothering about all these temperature, noise, power signals into consideration while going for design. This is the major difficulty in analog design. So we all know Moore's law, where Moore's law states that the number of transistors increases or doubles every 18 months. So you can see the number of transistors in 90s. So up to 1975, we are having a slow rise. But see here, after 1970 to 2000, the number of transistors in different processes are just in millions and billions. So here, since there are no more researchers and there is no more technological development is available towards analog VLSI, we are normally having the doubt that is analog VLSI design outdated. So this is not true, because as per survey, the total analog chip sales for 2002 is $39 billion, whereas it is $48 billion in 2004. So here, when working with a chip which is analog, we need good design practice, because when in the total chip, if analog occupies a very small percentage also, the overall system performance is decided by the small percentage of the analog component which is present in the chip. So here, when working with a system which consists of both digital and analog, the analog part decides the system performance. And here, most of the systems output are analog in nature. So here, even when we are working with the digital domain, one should have the ability to understand the interaction between the analog and digital domain is important. So before 1970s, most of the systems are analog designs, and after that, digital systems arrived. We know digital systems have more advantages. They are more accurate, simple, and there is less possibility for inclusion of noise. So with these advantages, this digital IC development grows little faster when compared with the analog ICs. So when we are coming to silicon VLSI technology advancement, that creates more market demand for these digital ICs. So the ultimate goal, yes, we have to create or develop a system on chip with mixed analog and digital circuitry. So this is a recent trend with mixed signals. So scaled CMOS and BiCMOS on the same. When working with the CMOS, we are fabricating PMOS and NMOS on the same substrate. When working with the BiCMOS, this BiCMOS is the combination of bipolar and MOS device. So combination of bipolar and MOS device on the same substrate. When working with the CMOS, P channel and N channel are fabricated on the same chip. So the recent trend is moving towards these two, scaled CMOS and BiCMOS. So we know VLSI microelectronics is an interdisciplinary field. One should have all the interdisciplinary knowledge to work on this field. So knowledge about the materials used, knowledge about the technology, CAD2 latest tools available for designing, and one should know about the applications for what we are going to use the system and what are all the system designs development. So everything should be integrated in this VLSI domain. So here comes the next important one. So when working with the analog IC design, we are focusing on mixed signals where we are integrating analog and digital. So this is a recent trend. So here, when working with the signal processing systems, there are two general categories, which in both the category, we are going to integrate both analog and digital on the same chip. So the first category is mixed analog and digital, and the second category is mixed digital analog. So here, the position of analog and digital is just exchanged. So this classification is with respect to the role of analog or digital they play on the chip. So the first one is mixed analog and digital. So here, the first one, analog part, provides the I/O interface to the core digital. So the core is digital and the input-output interface is analog. So you can say, along with the data converters, the another one major difficulty with this mixed signal is, we know all the real-time signals are analog nature. If the system is, the core is digital, then we need analog to digital converter, right? Similarly, if you want to give the output to the real world, again, you need a conversion from this digital to analog, right? So, when you are working with this analog ICs, you should be clear with the A to D converters and the D to A converters. So, along with the data converters, the interface circuits may include amplifiers, filters, compressors, power drivers, and sensor interfaces, etc. So here, these are located at the periphery because the analog devices occupies the I/O. So these are located at the periphery of the chip, but plays major role in the overall system. As we already discussed, if the system is with a small part of analog, then the performance of the small part of the analog decides the overall system performance. So these analog devices plays the major role. So here is an example where the interface transceiver, U interface transceiver with ISDN is given, where this provides the final link between the digital world of ISDN and the end user. So from the digital, it is converted to analog. All the components what we have described are given, and this digital data should be converted to analog, and it is again given to the end user. So this provides the path link between the ISDN and the end user. So the next one is mixed digital analog. So as we already discussed, this digital part provides the I/O and the core is analog, right? So when comparing with the mixed analog digital, this digital and analog interchange their roles, and this is the emerging trend, right? So one of the major application of mixed digital analog is cognitive neural systems, and pure analog systems also comes under this category, mixed digital analog. This comes under pure analog systems also comes under this category, right? So here, why this is the emerging trend and what is the advantages? Digital is used for handling the complexity with the I/O, because when we are working with the analog input, we are in need to convert that to digital, right? So here there is mismatching in speed, the conversion speed and the system which is in digital. So the conversion speed is the major drawback, and it is very difficult to choose a proper A to D, D to A converters, which plays major role. So here the digital is used for handling the complexity with the I/O. So this is the emerging trend. So this is the mixed signal neural processor for image data compression. So this is the example to understand mixed digital analog. You can see the digital data is given as input to the neural digital signal processing. From here, it is converted to analog by means of this A to D, D to A conversion. Then the analog signal processing system works. From that, again, it is converted to digital by means of this analog to digital conversion. So when it is given to the outside world, again, the digital form of output is given. So what are all the analog building blocks, basic building blocks of analog system? So current sources, current mirrors, single stage amplifiers, differential amplifiers, op-amps, comparators, voltage references, data converters, and switched capacitor circuits. These are the basic building blocks of analog IC. So what are all the challenges? So we know the speed increases up to 5 Gbps. Then when working with the analog system, we are having some difficulty with the PCB materials because they are having some limitations. So as per the complexity, it is very difficult to work with the PCB material, which is having its own limitations. So here, for overcoming this, they are often using interface chips. For example, Texas Instruments LVDS is one of the interface chip. So this has built-in pre-emphasis on the transmitter side and equalization on the receiver side. So when connecting PCB across motherboard, this Texas Instruments LVDS interface chip provides built-in facility which is required on the transmitter side and the receiver side. So here, the need to conserve power and silicon die area is another challenging open to analog circuit designers, power consumption and the area. Then when working with the highest speed networks, again clock and timing budgets. So if you want to increase the speed, the budget towards clock and timing should be with the minimum value. So in high-speed circuits, PCB layout is one of the last step. This is like the location in the real estate business, which is more important than anything. So here, the designer should do critical decisions for the placing or placement of an IC on a motherboard. So depends upon the location of the IC on the motherboard, the thickness of copper wire used, and we know the distance between the wires decides the noise. And they also includes capacitive effect over the circuit, crosstalks. So here, many of the IC suppliers provides evaluation boards, and based on the suppliers evaluation boards, the designers decides where to place the IC. Similarly, based on the supplier's data sheet, they will decide the copper clad and the fiberglass for PCB. So by going with the supplier's evaluation boards, the designer may feel convenience to find out the bugs. So there are design tools available for analog IC design in the market. So National Semiconductor developed Webench Designer tool. So this includes software algorithms, and they help the designer for easy designing. So here many powerful analog tools are merged, and they have designed the Webench Designer tool. So within seconds, by means of using this Webench Designer tool, the designer can able to calculate the power requirement. So the user can make value-based comparisons before committing to the design. So this is one of the major advantage of using Webench Designer tool. And here, this also provides suggestions for selecting and ordering of components for the breadboard. So this is another one advantage of Webench Designer tool. So here, this will provide the platform for combining the existing and the new tools. This can provide platform for integrating these two. When working with the analog design, normally the designers needs many weeks or even months to customize the design. So here, with the help of design tools like instrumentation amplifier common mode voltage calculator, which is INACMV calculator, instrumentation amplifier common mode voltage calculator. By means of using this tool, the designer can design with the minimum time, so that they can avoid the design problems when working with the common instrumentation amplifier. Normally, we are having design problems when working with the instrumentation amplifier. So we can avoid that by using this spreadsheet calculator, which is INACMV calculator. Right? This is one of the design tool which is developed by the national semiconductors when working with the instrumentation amplifiers. So the another one is Analog Devices provides a website which provides technical support to the design engineers, online technical support. So it is named as Engineer Zone. So this Engineer Zone offers RF tools like ADI SIM RF, which is used to provide the facility to calculate cascaded gain, noise figure, and total power consumption. Another one technical support is circuits from the lab. This is one of the tool which provides the proven reference designs, so that the designer can take any of the reference design and they can use it for their design. By means of taking the reference design from the website which is already proven, they can save their working time. So these are some of the technical supports available for analog circuits. So even with these design tools available for analog design, the failure rate is more in analog designs. Why more failure of analog designs? So what are all the reasons? So here analog circuitry stopped following Moore's law a long time ago, but that has not always helped. So here there is a gap between analog and digital dependability, and this gap is growing. So when there is a large gap between two technical domains, analog and digital, then the digital design appear to be winning because the analog part has more possibility for failure. The reason for failure is due to the older methods for verification and the design automation and verification methodologies are not that much available as that of your digital design. So older methods for design and verification and lagging of tools, design automation and verification is lagging for analog. So these are the major reasons for failure of analog designs. So as per the statement from the Siemens mentor, the analog blocks do account for a large percentage of chip failures. The reason he stated is due to high complexity and error-prone process, full custom design, limited systematic verification, and less automation when compared with digital. So the complexity is due to the consideration with the factors like temperature, noise, and power signal. And the inclusion of noise always leads to error. And there is need for full custom when working with analog because inclusion of more number of parameters constraints, and for verification only limited methodologies are available, and the automation tools are also not supporting as that of the digital. So we will see what are all the testability. Testability, limited systematic verification is the major drawback with the analog system failure, right? This is a major cause. So what are all the testability methods available for analog? So in working with the analog VLSI circuits and internal circuit nodes, analog testing, digital testing, and mixed signal testing are available. So pure analog means we are providing analog input and taking the output. Mixed signal is when working with the digital that should be converted to analog and it is processed. Again, that should be converted to digital and it is given as digital to the output. Or if we are working with the analog, it is given in the form of digital, and the digital core works, and the digital output is given as digital if required. Otherwise, it is again converted to analog and it is processed with the system. So digital means there are, when working with the digital ICs, we are having different design for testability. There are macro test, boundary scan techniques are available, self-tests are available, and more number of tests are available for testing digital ICs. When working with the analog ICs, we know since there are more possibilities for inclusion of noise, there is more possibility for the occurrence of fault in case of analog. So here, the catastrophic fault testing is similar to that of digital, and there are ad hoc test approaches available for analog IC testing, and few new approaches are also available, and CAD tools are used for the new approaches. So here, the fault modeling and simulation is another one important thing when we are working with the analog ICs. There are physical faults where if there is a pinhole in oxide layer or the doping concentration is not in the acceptable ratio, then that can create physical fault. So the fault on the whole change behavior of the circuit, where number of minor faults combined, and that leads to failure of the entire system. And the basic fault categories can be classified into two. One is a hard fault and the other one is the soft fault. The catastrophic faults are hard faults, where the parametric and deviation faults are soft faults. So catastrophic or hard faults means these are dominated faults. So these are randomly occurring, and these are by structural deformation. So you can take for example open interconnection or short interconnection. So if there is open or short, that can lead to stuck faults, stuck open or stuck closed faults. So if there is a large dust particle on the wafer, then that can create hard fault. So the second category of faults are soft faults. So these faults are very difficult to identify. For example, if there is a tiny dust particle on the wafer, that is a soft fault. So it is very, very difficult to identify this parametric or deviation faults. Hard faults are easy to identify. The other faults are multiple faults, non-catastrophic errors, etc. So to detect the faults by simulation, we are going for the fault simulation models where we need test patterns. So if these test patterns are applied to the fault model, how much faults are identified? That leads to fault coverage. So there are two deviation faults. One is global and the other one is local deviation. So there are number of mixed signal simulators available in today's scenario. SMASH, SOBER, and featuring macro modeling, Monte Carlo analysis are few of the examples. So here we are going to see about how the testability is improved, or what are the methods available in today's scenario. So here, controllability and observability. These are the two important terms which are related with testing. So how one should able to control the flow of signals, and how easy is the observation of signal in the circuit. So here, embedded nodes for testing of analog or mixed circuits. So here, an example is given with the RLC circuits. So analog circuit with multiple deviation faults. You can take this circuit as an example: resistor, inductor, and capacitor. So we are providing input through this and we are taking output across. So here, This P1 and P2 are the test points by means of observing the values at this point, test point P1 and P2, one can able to observe the fault. So here there are ad hoc methods available, and few general guidelines are included here in the presentation. So there are two fundamental approaches. One is looks only for answers to test the problems of a specific circuit. So this is called ad hoc approach, problems of a specific circuit. Then starts immediately at the beginning of the design. So while designing the circuit, when the process starts, the testing is also parallelly started. So the hierarchical approach is with the macro testing. So here the drawback of this hierarchical approach is when obtaining the observability, controllability, and we need isolation. So when working with the large circuit, we have to isolate the circuits where we need to observe and control the signals. So isolation of circuits is must when we are working with this macro testing. But when working with the ad hoc approach, there is no need of isolation of circuits. Here we are just adding probes. So even if the chip is already manufactured, you can add a probe point and you can monitor the values needed to monitor by means of using some meters or something else, just by means of inclusion of a probe point. So this is fast, and there is no need of any isolation or separation of circuit. So this is cheap. But there is a drawback with the ad hoc approach, which means we should provide some physical points for inclusion of probe points. So that may increase chip area, and the node capacitance also increases when a probe is included, and this needs buffering. So the most frequently used approach of partitioning a complex chip is explained here with macro testing. You can see an op-amp with R1, R2, and we are providing input through this. This is the reference voltage. So here the output is measured from this N4. So we can access N1 where we are providing input, and we can access N2 where we are providing the reference signal, and we can access N4 from where we are taking the output. Right? So here we are going to include a point at this N3, right? But we are having access over this N1, N2, and N4, right? So we can able to measure closed loop voltage gain, offset voltage, slew rate, and we can able to measure the RL conditions of the circuit. So we can partition the circuits, and we can able to measure the values of the given circuit. So here for increasing the observability, as we already said, observability means how easily the designer can observe the flow of signals, right? So here to increase the observability, one can add test point, one may combine test point, or buffered high impedance microprobes may be used, or there may be built-in switches. So here you can take an example circuit. So see here, the switches, built-in switches are given. So this is the circuit. So the input, primary inputs are given, and from these the primary outputs are available. So here these two are just connectors. So here the built-in switches are available by means of viewing through the switches. One can able to identify, or one can able to observe the value or the signal which flows through these two. So by means of observing the output of this switch, right, one can able to understand whether the fault is present in filter. So you know what is the input and you know what is the output. The designer should know what is the given input and what is the expected output. So by means of observing the output at this point, the designer can able to identify whether fault is present in this part. If there is no fault, then he may go through the built-in switch which is used here. So by means of observing the output from the op-amp, the designer may know what is the input and what is the expected output. So by measuring the output at this point, the designer can able to understand whether the fault is with the op-amp circuit. So the filter is monitored by means of this. The working of op-amp or whether there is fault in the op-amp is monitored by this. And if this input is given and by means of taking the output at this point, one can able to identify whether the fault is with the comparator circuit. So just by inclusion of two switches, one can easily observe the flow of signal within the circuit. So if you want to increase the controllability, the input be isolated from the output of the previous stage. So by means of providing a probe point, one can isolate the input and the previous output. And the other technique which is used for increasing controllability is by means of using laser beam. But when working with the laser beam, you have to remove the particular part from the board. Then you have to do the test and then you have to again fix with the motherboard. That is the problem with the laser beam. So the simple method is by means of using gates and analog multiplexers. So here when working with just simple gates and analog multiplexers, when testing is completed, just it is automatically connected with the circuit. While working with the testing mode, you can use that with the testing mode. After at the time it disconnects. Then after testing is completed, it returns to the normal mode. This is the advantage. So there are scanning techniques available. So here there are a number of different approaches are available. So the basic one is with the scan technique. The basic one is with the shift registers. So by means of connecting shift registers, one can able to increase the observability and the controllability. So this is the basic method in which the shift registers are used for increasing the controllability and observability. So here, what are the drawbacks? Even this is simple. Just by connecting shift registers, we can increase. But what is the drawback with this basic inclusion of shift registers in order to increase controllability and observability? Yes, more number of input and output pins are required. Additional input and output pins are required. And when shift registers are included into the structure, the testing, we know when there is inclusion of shift registers, just you imagine you are working with a 64-bit model. So you need you can able to calculate the size of the shift registers needed for testing. So the inclusion of shift registers in the architecture may increase the size, and the testing time is also very long. This is the drawback with the scan technique, which is with the shift registers. So here the CAD tools. So the task of converting performance specifications into complete circuit diagram, including device sizes and passive elements. What are the values we need to connect? The complete task is done by the CAD tools, from specifications to the value of passive elements in the circuit. So here, the characteristics of analog design is examined at two different levels. One is system level and the other one is cell level. So here, these two are two dissimilar tasks. So the circuit design task is specifying the performance of primitive, whereas physical design is talking about the geometry. So the divide and conquer is the hierarchical decomposition, where the designer can just simply breaks down the design task into several sub-design tasks. So you can see different sub-design tasks: architectural level, then evaluation, then circuit level evaluation, then layout level evaluation. So the complete design is divided into parallel sub-design tasks. And system level analog design is just broken down into number of individual stages. So here is an example with the A to D converter pipelined. So the first stage, the specifications, then what is with the basic components, and from that it just divides up to the basic component. Here the comparator circuit, op-amp circuit, and the switch circuits are the basic building blocks of the circuit, and we are just breaking down the architecture to individual stages, the basic component. VLSI technology trends now it is moving towards frequency and power trend. There are so many challenges when working with scaling. Scaling is done with transistor, interconnect, capacitive and inductive coupling, and leakage. These are the challenges when working with scaling. So, how the processor frequency trend is in today's scenario is analyzed here with the help of this graphs. So here you can see the frequency. So it doubles. See the duration. So from here to here, just it doubles in every generation. So Pentium 2, 3, and 4. And similarly, the number of gates per clock, reduces by 25%. So the frequency doubles in each generation. So what is the conclusion from the entire presentation? Is the analog IC design is not outdated one because of the lagging in design methodology and verification tools, and also the lagging in CAD tools leads to the failure of design. So when working with the mixed signal also, even the analog part is very small, then the overall performance is affected by this small part of analog design, and the responsibility, overall responsibility is with the analog part. So the design of analog part is little bit difficult because we need to consider many of the parameters like temperature, noise, and power signal. So more constraints are there for analog part, even it is with a small percentage, it plays the major role when we are working with a mixed signal also. Then when working with the analog IC, interdisciplinary knowledge is necessary, which is not required for digital IC. Hope we all know when working with the digital design, the designer, even the designer has no knowledge about what is inside the module, can design the module. Without knowing what is inside the multiplexer, one can design multiplexer. If he knows the basic operation, one can design. But the design with the analog circuit is not that much simple because we are working with the continuous signal where we are having more possibility for inclusion of noise, where there is chances for variation of input itself due to temperature, noise, or there may be variation due to power signals. So, with all these constraints, the design of analog circuit is little bit complex. And we are not having modernized tools like which are available for digital counterpart. So lagging of tools is the another major constraint when we are working with the analog IC design. These are the reasons for uh, failure of analog designs. But now in recent days, again there is a tremendous growth with mixed signal processing, and we are having few platforms for designing the analog circuits. The few companies provides the platform and guideline for working in analog IC domain. So the next 10 years, yes, we are going to traveling with the scaling technologies, and the analog designers should focus on the scope of variables where they have to manage, and what are all the circuit constraints, and we have to concentrate on the extreme sensitivities and the quality of results. So since even the analog part is with a small percentage in the overall system, that small percentage decides the overall performance, right? So the quality of results to make the analog design better these should be the main focus of analog designers. So this is what I want to share with you people. If you have any clarifications, you can ask. Otherwise, we will see the sample research work, which is the continuation of this session.
Participants, if you have any doubts till now means you can ask.
Okay, we will proceed with the sample research work. So in image processing, we need to convert the image into digitized form. So here, based on this digital information, we are going to do some basic operations in order to improve the quality of the image. So in image processing, image compression is one of the vital role. So here, the objective of the image compression is to minimize the data which is insignificant and which is redundant in nature. So the need for image compression is to make faster communication and to reduce the memory which is required for storage, and in order to reduce the transmission cost. So here we are going to see two different works for image compression. So we know there are two types of image compression. One is lossless and the other one is lossy. So here the transform based compression is taken, which is the best compression method for lossy type. So here wavelet transform DWT is used for the compression. So here this decomposes a signal into set of basis functions. So the advantage with the wavelet transform is that can be represented both in time domain and frequency domain, so that we can get more detailed signals, more accurate. So here the advantage is high compression ratio, and there are straightforward computation methods available. So these are the features of DWT: adaptive time frequency windows, and computational complexity is reduced, lesser aliasing distortion, inbuilt scalability, then well-organized implementation, in-place computation. Almost all domains are given here, the applications of DWT. So one among that is image compression. So here for the implementation of DWT, there are two methods. One is convolution and the other one is lifting scheme. Lifting scheme is just advantageous when compared with the convolution, because in convolution there are more number of operations. So this is just based on Euclidean algorithm. The factorization is done, and just the wavelet, the polyphase matrix can be factorized into the upper and lower triangular matrices just by means of few, just 3 steps. So the coefficients can be split into odd and even, and whether there are even coefficients, odd coefficients present in the even can be predicted, and they can be updated again. So by means of simple 3 steps, here factorization of polyphase matrix of the wavelet filter can be divided into sequence of alternating upper and triangular matrices, right? So the advantage is less number of computations. We know with convolution there are more number of computations. So complexity is reduced, in-place data manipulation, and perfect reconstruction is also possible with this. Why we are going with the here the complete work is related with the Gbps wavelet. In that, the concentration is given towards 9/7 filter and 6/10 filter. Why the choice of filter and wavelet is with this is the JPEG 2000 is a popular image compression standard, and in JPEG 2000 these filters are available. So the choice of filter is Gbps 9/7 and 6/10 filter for the work. So here the area efficient CSD based VLSI architecture is proposed. So we know CSD is for the purpose of removing multipliers. So in VLSI, we know when strong computational units are replaced by weak computational units, we can able to reduce the complexity. So in this work, we are providing image as the input, and this image can be decomposed into 4 quadrants, right? So low, low, high, low, high, and high. So among this, The LL quadrant consists of more information, and this part alone is transmitted. And in the receiver side, this can be used for the reconstruction of the original image. This is a overall block diagram of this work. So here, the entire architecture is designed by removing the multiplier, and we are going to adopt CSD architecture for this part, where the mathematical modeling VLSI part is involved. And in the second part, CSD with harness rule is used. So how we are going to attain the target? So image input, and we are taking output as image, but in between we are going to work with the digital part. So here in the CSD lifting DWT method, the filter coefficients are first flipped and multiplied by 256 in order to convert them to integer form. Then for wherever there are negative numbers in the coefficient values, we are going to take 2's complement representation, and we are going to take CSD representation for the integers. And here, since we are from VLSI domain, hope you people know CSD is taken here in order to convert the whole structure into multiplier less. So here, multiplication is multiplier less architecture. We are going to design multiplier less architecture. So here, the multiplication is done just by adding the number of product terms according to the number of ones present in the representation. So according to the non-zero bit position, wherever there are ones. So according to the ones position of ones, we are going to add the product terms. So here, the canonical sign digit representation is a special case where there is no two consecutive non-zero bits. So here, minimum possible number of non-zero. So the name canonical is given. So this is the algorithm for CSD representation. Hope you all are familiar. So the methodology or the algorithm says that from the rightmost, you have to check for the consecutive ones. If there is consecutive one, then the first consecutive one should be represented in its complement form. Then the remaining ones, right? When there is consecutive one, you first take the first consecutive one and complement it, and the remaining all ones are converted as zeros, and the next digit after the consecutive one should be flipped. Here, flipped in the sense, if it is 1, you have to convert it to 0. If it is 0, you have to convert it to 1. So this is the structure of CSD multiplication. So here is the example what we have discussed with the algorithm. So here in the DWT architecture with 9-7 filter, there are 4 coefficients, alpha, beta, gamma, and delta. And each coefficient is having its value. So these mathematical values are available as per the choice of your wavelet filters. So here the filter coefficient is minus 0.6305 and we are taking the input. Since the image considered for the work is gray image, the range of grayscale varies from 0 to 255. So any one of the pixel value within this 255, 0 to 255 is the input. So here let the input be 178 for example. So here for the filter coefficient, you just convert this value to integer form and then you have to convert this to the equivalent canonical sign digit. So just as usual, you convert this to integer by means of flipping and multiply by 256. Then you have to convert that to equivalent CST so that you can get alpha inverse of this value. So here, if you take 6305 and multiplication with 0.6305, if you multiply this with 256, you will get the value as 161.408. And then you have to do the conversion with zeros and ones, convert that to binary, so that you can get the value as 101401. Then you have to find out the 2's complement. Since this is a negative number, you have to do the conversion to 2's complement. Then you take CST. So in the representation, after finding out the 2's complement, you will get 0, 1, 0, 5 number of ones. So you have to first find out the consecutive ones, which is the rightmost bit. So keep the rightmost bit with the flip. Then you have to convert all the bits to zeros. Then again you have to make conversion with this bit. Then you have to flip this. So you will get the value like this. So here, this is the 9th position. This is the 11th position. And this is the 16th position, right? So here, just you convert 178 to binary value. So you will get this. So based upon the position of ones in the filter coefficient, the input has to be right shifted and added, right? So here the position of 1 in the filter coefficient is, this is 9th, this is 11th, and this is 16th. So the output is minus 2 to the power minus 9. So this is the 9th position, this is the 11th position, and this is the 16th position. This much number of times the input has to be right shifted. This is the input. So here if the filter coefficient is negative, then you have to take the 2's complement as the output. So this is the structure of modified DPP, where the multiplier which is normally given is replaced by the CST multiplier. So the results shows that here the image should be converted to pixels, right? So each time the stripe width is considered as 4. And we are providing input based on the pixel values. So based on the comparison, the proposed work has no multipliers and the number of adders increases to 24 S, where the strip width is 4, whereas in all the previous cases it is 16. So there is a rise in adder, but 10 into S. So if the stripe width is 4 for this work, then you need 40 of the existing where it is with 0. Then there is no much difference in the registers and buffers, the transposition buffers and the temporal buffers. And here the critical path is also reduced to 2 TA adder time. So the remaining comparisons with power, delay. So power is reduced to a minimum value, but the delay is very much reduced, and there is also a medium memory utilization requirement is reduced. So when compared with the existing, there is a large reduction in delay and a minimum power consumption, and there is a moderate reduction in memory usage is possible. So here another one modification with the digital part is with the harness rule. So we know canonical sign digit is with the minimum number of ones. When working with the multiplication, if there are more number of zeros, then there is no switching or there is no need of working with that part. So in order to reduce that, we are going for canonical sign digit with a minimum number of ones. So when minimum number of non-zero bits, we can reduce the computational activity, right? So here we are going for the CST with the harness rule. So here harness rule is based on the distance between the position of non-zero digits. So the previous canonical sign digit part is with the position of non-zero digits. Here harness rule is related with the distance between the position of non-zero bits. So here for providing input from the image to the digital part, we are using interlaced read scan technique. So by means of this scan technique, we can able to reduce the memory, transposing memory. And here the multiplication of filter coefficient is just carried out by a shift-add algorithm. So we can able to provide high speed, less power consumption. So here we are going to use a shift-add algorithm, right? So shifting is done based on the position of number of ones right and left of the decimal point. So here all the coefficients are with the floating points. Here the shifting is done based on the position of number of ones in the left and the right of the decimal point. So here the multiplier complexity is reduced when working with the canonical sign digit with the harness rule. So these are the one level, one dimensional 9/7 filter mode of lifting DWT. So here detail coefficients D0, S1, H0, L1. So high coefficients and low coefficients with alpha, beta, gamma, and delta. So the value of all the four coefficients for Dobitsch's 9/7 filter is given here. Minus 1.586, minus 0.052, then plus 0.88, then the value of delta S plus 0.4435, and these are scaling coefficients K0 and K1. So this is the system diagram of the proposed 2D DWT, where the input pixel values for the corresponding image is given as input, and the first one-dimensional DWT is here. When input pixels are given, this can do the first level of decomposition and provides the high coefficient and the low coefficient. Similarly, the input pixel to the first one-dimensional DWT provides the low and high coefficient. And both the high coefficients are given to the second 1D DWT, which provides next level of decomposition. And the low coefficients from both the first 1D DWT are given as input to the second 1D DWT. So from the second level, we can able to have the four decomposed values of images LL, LH, HL, and HH. So in this contains more information, and again the reconstruction is possible. Instead of transmitting the full image, the transmission is done with the help of this LL alone. And in the reconstruction, in the receiver side, the image is reconstructed with this quadrant of image alone. The four among the all four quadrants, this alone is considered for reconstruction. So here in the first stage 1D DWT, the one of the pixel per clock is given as input. So after getting 3 pixels, the high frequency output is calculated. When 2 high frequency outputs are available, first 3 pixels are given, and this can compute or do first level of decomposition and provides high. Then when 2 high coefficients are available, this can able to start its computation. So after here, while doing the decomposition process, in order to do multiplication, shift add algorithm is used. And here in the shift add, carry save adder is used for the addition purpose. So this is the structure of first stage 1D DWT, where the input is given. After getting 3 pixel values, the harness rule based CST MAC can do the multiplication process. Without a multiplier, this can perform multiplication operation, and the output is given with the low coefficient and high coefficient. The first level of decomposition with the help of harness rule based CST MAC. Then in the second stage, after receiving high and low inputs from the first level of 1D DWT, that can be again split into 4 quadrants with the HH, HL, LH, and LL. So here, the only exception is after the computation from the first level, 2 high frequency signals can be grouped and given to the second stage 1D DWT, and the 2 low coefficients can be combined, and then they can be given as input to the second 1D DWT. So here, this is the structure. So here, after getting LL from the 1D DWT and HH from the 1D DWT. So there are 4 inputs, right? So we need 4 registers, and that can be given as input to the second level of 1D DWT. So this is also harness rule based MAC. Then from that we can able to get the quadrant subbands HH and HL. Similarly, the another second stage 1D DWT provides LL and LH. So this is a harness rule based CSD MAC where we are providing input and we are getting output from this. So the list of CSD values for the 4 coefficients of 97 Dobitsch's wavelet and the corresponding CSD values are given here. So the methodology for adopting harness rule with the CSD is given here. So G is the input image pixel and the coefficients, multiplier coefficients are considered here as alpha and beta. So how harness rule is adopted? So here the filter coefficient alpha is 0.1, 0.1001010. So for this coefficient, you have to take CSD values. Then based on this CSD, position of 1 decides how many times it has to be shifted and added. Right? The input has to be shifted and added is the CSD method. So based on the position of ones, how the input has to be shifted. So 2 to the power 1 from here, 2 to the power 1, 2 to the power minus 1, 2 to the power 3, 2 to the power 5, 2 to the power 7. So 1, 3, 5, 7. So all the values are here 1 cap, 1 cap, 1 cap. So we are using minus, but here it is 1. So we are using plus 1. Right? So here the input pixel has to be left shifted once since it is 1. And it is right shifted once, right shifted 3 times, right shifted 5 times, right shifted 7 times. So the input pixel is this much times shifted and added to get the output when we are working with the CSD. Right? Now we are going to adopt harness rule with the CSD. Right? So you can just see how many number of shifters are needed here. Shift and add 1, 2, 2 plus 3, 5, 5 plus 5, 10, 10 plus 7, 17 shifts and add. 1, 2, 3, 4, 4 times. Right? So now we are going for adapting harness rule. So here harness rule is applicable when the coefficient value is already known, right? So here we know the filter coefficients already. So we are going to do adopt the harness rule for our work. So here in this harness rule, when the value is signed integer and float multiplication with the negative value, the representation in the CSD is minus g into 2 to the power minus 2. So you can take the distance between the two ones, right? So the distance between the two ones and the distance between the two ones, right? So here minus g into 2 to the power minus 2 plus g, you will get g1. Then this g1 is used for the next computation. So g1 into, again the distance between the two. So 2 to the power minus 2 plus g, you will get the next value which is g2, and you have to use this for the next computation. Again the distance between the two ones is 2 times. So 2 bits. So you can use 2 to the power minus 2 equal to g3. So here this value, the last one is considered as it is, the position of ones, 2 times, 2 times, 2 times. And here this G3 is just multiplied by 2 to the power 1. You can get the intermediate value as alpha 1, and it should be added with the 0 so that you can get alpha out, which is your required output. So here, first, this 2 to the power, these are between the distance between the two ones, right? So 2 to the power minus 2, 2 to the power minus 2, and this is 2 to the power minus 2. So we know this is 2 power 0 and this is 2 power 1, right? So here, this 2 to the power minus 1 represent the position of the first one, where the first one. So here, this after getting this alpha 1, there is no need of adding the intermediate values because this is the last one. So no need to add any value. Here all the values are added with the input because these are just intermediate results. But when working with this 2 to the power minus 1, this represents the position of the first one. So there is no need of adding intermediate value, right? So here, this alpha 1 is for a fractional part, and this is for integer part. Here, when integer part is considered, this 2 to the power 0 is with 0. So when you are multiplying it with 0, you can get a 0 value. So this is for fractional part. This is for integer part, so that you can get the output as alpha 1. Okay? So now you can calculate how many number of shifters and adders are needed. So here 2 times, 2 times, 2 times, so 6 times, plus 1, 7 times. So instead of 17, you need just 7 shifters. And the number of adders is also just 1, 2, 3. And here there is an adder which is required for adding the fractional part with the integer part. So 1, 2, 3, here 1, 4. So just 4 adders and 7 shifters instead of 1, 2, 3, 4. 4 adders and 17 shifters. This is the reduction. So when this is again explained for the coefficient beta. So based on the number of distance between the non-zero bits, we can just using this. So the distance between the two ones is just minus 3. So we are using this. This decides the position of the first one. So we are getting this. So 3 plus 4, 7. Here it is 7 plus 4, 11 shifters. So this is the reduction. So here when working with the harness rule and CSD, we can able to achieve the improvement in power, right? So the area is also reduced. So the power reduction is 35%, and the cell area is reduced by 27% when compared with the CSD architecture, right? So in this work, we are providing image as the input, and we are taking output in the form of image, but the entire core is with the digital part, where we are adapting the CSD and harness rule with the CSD. This is one of the best example for the mixed signal processing. So Thank you. If you are having any queries, you can raise.
Thank you, ma'am. Dear participants, this is the time for question and answer session. If you have any doubts or queries, means you can ask now. You can post your question in chat box or else unmute yourself and discuss with the resource person. Your mic was enabled now. I think there is no queries from participant sides, ma'am.
Okay, Bhaskar, we can finish.
Yes, ma'am. The roots of all goodness lie in the soil of appreciation. In this way, I would like to thank our today's resource person, Dr. V. Geeta, Associate Professor, Department of Electronics and Communication Engineering, Kongu Engineering College, Erode, for providing a wonderful session on the topic of role of analog signal processing in a VLSI design and a sample research work in a DWT image processing. On behalf of organizing team and Kumulnadu College of Engineering and Technology, we once again thank you so much, ma'am.
Thank you, Bhaskar. I want to say a few words in this forum. This is my immense pleasure for participating in this FDP. I want to thank the management, the principal, and the organizers of Kongunadu College of Engineering and Technology, Trichy, for providing me the opportunity to share my knowledge in this VLSI domain. And I want to thank my friend Yuvaraj for providing me the opportunity to share my knowledge in this VLSI domain. I request the participants to contribute something in the research area of analog IC. Even though it is a little bit difficult, you may have wide opportunities when you start working in this path. Thank you once again for providing me the opportunity. Thank you, one and all.
Thank you, ma'am. Thank you so much.
Thank you. May I leave the.
Yes, ma'am, you can leave now.
Thank you.
Thank you.
Thank you.
Participants, the day 2 session 2 attendance and the feedback link is posted in chat box. It will be open up to 30 minutes only, so kindly fill it soon. And while filling the feedback form, kindly select your respective FTP ID. The FTP ID document is once again attached in the chat box. Kindly check that. Thank you all. And all the participants are requested to join the tomorrow session at 10 a.m. sharply. Thank you.